Okay, we'll look into optimization algorithms for sparse optimization in more detail in this section. In particular, we will discuss algorithms for convex optimization. This is the table of contents. First, we will review basics of convex optimization. Then, we will define proximal operators which are important to develop fast algorithms for convex optimization, including the L1 norm. By using proximal operators, we introduce proximal splitting method for L1 optimization and proximal gradient methods for L1 regularization. Also, we will consider generalized lasso and the ADMM algorithm. So let's begin with basics of convex optimization. This is the L1 optimization problem we consider here. As we have seen, by using CVX on MATLAB, we can easily solve this problem by very simple coding like this. The CVX is very useful for small or middle scale problems. However, it's not that useful for large scale problems like image processing or real-time applications for control systems. Therefore, we need to build an efficient algorithm by yourself for your specific problem. This is the motivation to look into convex optimization theory in this section to develop fast algorithms for our problems. So let's review convex optimization briefly. First, we define convex sets. Let C be a subset of Rn. C is said to be a convex set if this inclusion holds for any vectors x and y in C and for any real number t in this interval. The left figure is convex since the line between any x and y lies in this set. On the other hand, the right-hand side is non-convex since the line between x and y goes outside this set. Then we will define the effective domain. The effective domain of a function from Rn to extended real numbers is defined by this. Namely, domain f is the set in Rn on which the value of f is finite. For example, let's consider the indicator function defined by this. Then, by definition, the effective domain of the indicator function is the set of x such that the L2 norm is less than 1. This figure illustrates the indicator function and the effective domain C. Now, let's define convex functions. Let f be a function from Rn to the extended real numbers. The function f is said to be a convex function if this inequality holds. For any vectors x and y in domain f and for any real number t between 0 and 1. These graphs show convex and non-convex functions. As you can see, non-convex function has a part where the line between x and y is below the curve. So this is a non-convex function. The epigraph is also important in convex optimization. The epigraph epi of f of function f is defined by this. That is, the epigraph is the region above the graph f of x, like this. So, this region is epigraph. We can define some properties of a function by using its epigraph. First, a function is convex if and only if its epigraph is a convex set. Also, a function is closed if and only if the epigraph is a closed set. A function is proper if and only if the epigraph is non-empty. Now you can easily understand these properties by the epigraph. Now we formulate a convex optimization problem in a general form. Let f, a function from Rn to the extended real numbers, be a proper, closed, and convex function, and C in Rn be a closed convex set. Then, a convex optimization problem is a problem to find a vector x asterisk in Rn that minimizes the function f of x over the set C. The problem is briefly written as this. In this problem, the function f of x is called a cost function or an objective function. The set C is called a constraint set or a feasible set. The entries of C is called feasible solutions, and the inclusion x in C is called a constraint. I believe these words are familiar with you. Let's review notation in optimization. The minimum value of a cost function is written as mean x in C f of x. The minimizer, or the set of minimizers, is described by using argmin like this. Namely, minimize f of x subject to x in C. This is a minimization problem or optimization problem. Mean fx, this is the minimum value, and argmin f of x, this is a minimizer or the set of minimizers. We will use the notation throughout this lecture. In general optimization programs, there are two types of solutions, namely global minimizers and local minimizers. A local minimizer is defined as follows. There exists an open set B that contains a feasible solution x bar in C and domain f such that f of x is greater than f of x bar for any x in B and C. On the other hand, a global minimizer is a feasible solution x asterisk in C that satisfies this inequality for any x in C. I will explain local and global minimizers using these graphs. The left-hand side shows a convex function whose local minimizer is also a global minimizer. On the other hand, the right-hand side is not a convex function, and the local minimizer x bar is different from the global minimizer x asterisk. For convex optimization, we have the following theorem. For the convex optimization problem given by this, any local minimizer is, if it exists, a global minimizer, and the set of global minimizers is a convex set. From this theorem, for convex optimization problems, you just need to find a local minimizer, which is consequently a global minimizer. Here, we look into convex functions more precisely. We define two kinds of convex functions, strictly and strongly convex functions. Let f be a proper function. The function f is said to be a strictly convex function if for any x and y in domain f with x is not equal to y and any t between 0 and t, this strict inequality holds. Next, the function f is said to be a strongly convex function if there exists beta positive such that for any x and y in domain f and any t between 0 and 1, this inequality holds. The constant beta is called a modulus. For strongly convex function, we have this theorem. Assume f is a proper closed and strongly convex function with modulus beta. Then f has the unique minimizer x asterisk in domain f, that is, for all x in domain f such that x is not equal to x asterisk, fx is strictly greater than fx asterisk. Moreover, for any x in domain f, we have this inequality. This is an important property of strongly convex functions, and this is used to define the proximal operator, as we will see in the next section. Now, we investigate proximal operators. A proximal operator of a function is defined as this. Let f Rn from the extended real numbers be a proper closed and convex function. The proximal operator prox gamma f with parameter gamma positive is defined by this equation. Now, let's look at the parameter gamma. If gamma is infinity, then the proximal operator becomes a minimizer of f, if it exists. That is, prox gamma f is arguing if gamma is infinity. On the contrary, if gamma is 0, then the proximal operator becomes the projection onto the set domain f. And we use a positive gamma, the proximal operator is a mixture of those. This picture illustrates the proximal operator as a translation operator. Let us consider a point V outside of domain f. If gamma is infinity, then V is directly moved to the minimizer. If gamma is 0, V is projected onto domain f. And the proximal operator is a mixture of these. Also, if V is inside domain f, its proximal operator moves V towards the minimizer like this. I will further continue an illustrative explanation of the proximal operator. This is a picture taken in IIT Bombay, Indian Institute of Technology, Bombay. I need to cross this street because I want to go to a chai restaurant over there. But this street is very heavy. There are a lot of rickshaws, trucks, and motorbikes. This is the crossing the street problem in India. That is, if I cannot cross the heavy street, I cannot go anywhere. I illustrate the problem here. I am here. I want to go to the chai restaurant here in the domain F. Many IIT students and faculty go like this. Since they are professional, that is, they go straight to the optimal point. On the contrary, at the first time I crossed the street like this, because I'm a beginner. This is the minimum time control to get to the safe domain F, or projection onto domain F since gamma is 0 in this case. But I became accustomed to the heavy street. I gained the parameter gamma and crossed the street like this. This is the proximal operator, more proximal to the goal than the projection. But please remember that too large gamma may lead to disaster. Now we describe the proximal algorithm using the proximal operator. As initialization, give an initial vector x0 and positive numbers gamma 0, gamma 1, gamma 2, and so on. Then iteration. For k is 0, 1, 2, do xk plus 1 is equal to prox gamma kf xk. That's it. We just apply the proximal operator iteratively. The algorithm minimizes the strongly convex function of g of k defined by this at each step k, which is an approximation of f that may not be strongly convex. This is the proximal algorithm. For the convergence of the proximal algorithm, we have this theorem. Suppose that the parameter sequence gamma k satisfies gamma k positive for all k, and the sum of gamma k is infinity. Then the vector sequence xk generated by the proximal algorithm of this converges to one of the minimizers of f for any initial vector x0. The proximal algorithm is, however, useful just for specific functions. That is, to use the proximal algorithm, the proximal operator needs to be obtained in a closed form to derive an efficient algorithm. A proximable function is a function that has a closed form proximal operator. It is well known that the following functions are proximable: quadratic functions including the L2 norm, indicator functions, and the L1 norm. Let's look at these functions. First, quadratic functions. We consider the quadratic function of this, where phi is a positive definite matrix. The proximal operator of f is given by this. Since gamma is positive, this matrix is invertible. Now we obtain a closed form representation of proximal operator f for a quadratic function of this. Next, let's consider indicator function. An indicator function is defined as this. For a subset C in Rn, the indicator function is defined by this. Namely, if x is in C, then the indicator function is 0. On the other hand, if x is not in C, then the indicator function returns the infinity. This is the indicator function. If C is non-empty, closed, and convex, then the indicator function is a proper closed and convex function. This is a graph of an indicator function on C. The proximal operator of indicator function ICX is given by this, where pi c is the projection operator on the non-empty closed and convex set C. We now understand that the proximal operator of an indicator function on C is a projection operator to C. Finally, let's consider the L1 norm. The proximal operator of the L1 norm has a closed form of this, where S gamma is the soft thresholding operator defined by this. This picture shows the graph of the soft thresholding operator. This is a piecewise linear function like this. As we will see, the soft thresholding operator plays very important role in algorithms for sparse optimization.